In this video, I want to introduce to you the fundamental theorem of analytic functions. Fundamental theorem sounds like an important theorem, and it is. It could be used to compute complex integration that we've been doing in the past in a brand new way, a much easier way. So let's take a look at this theorem. Okay, so let's say we have some domain D in the complex plane, and we have some continuous complex function f. We say the function has a primitive if there's an analytic function capital F such that the derivative is the original function f, right? So in calculus class, we'll call these antiderivatives. In the complex setting, we use the word primitive. It means the same thing. Okay, so here's the theorem. If you have a continuous function f on some domain D, and if little f has a primitive capital F on D, then along any curve that's sitting inside of the domain D, we can compute the path integral by looking at the difference of the primitive evaluated at the beginning and the end of the path. Now, this very much has the flavor of the fundamental theorem of calculus, where we evaluate the Riemann integral, and the area under the curve is exactly the difference of the antiderivative evaluated at the endpoints of the integration. But if you think a little bit about it, like this seems crazy that it's true, because in the real line, there's really only one way to get from A to B through that interval from A to B. But in the complex plane, the path is two-dimensional. So you could go any which way you want. You can travel that way, you can travel this way, taking completely different path. The path integral is still going to give you the same value at the end, which is crazy to me that it could be true. So some notes about this theorem. The integral only depends on the endpoints. So the path you take in between doesn't matter. We don't have to do that actual path integrals. We just have to find the antiderivative and just look at the endpoints. This is a different way to compute that integral. There's a big assumption that's hidden here. And the assumption is that the primitive must exist. With the fundamental theorem of calculus, the primitive was, or the antiderivative was the area function underneath the curve. It's not necessarily true that we are always able to find primitive in the complex setting. So the question becomes, under what assumption can we find a primitive? Okay, so let's do an example of computing something like this. So let's say gamma is a curve that's connecting from 0 to 1 plus I. I use the example of the straight line from 0 to 1 plus I, but now I know that I can take any path I want. And then let's say I want to integrate the continuous function z squared, which has a primitive z cubed over 3. So if we want to integrate along this path, and I'm kind of abusing the notation a little bit now, because if this fundamental theorem of analytic function is true, then it really doesn't matter what path we take. I'm just going to put the beginning and end points in the limits. It doesn't choose your favorite curve connecting those two, and it'll give you the same value in the end. So how do we compute it? We just look at that the primitive evaluated at 0 and 1 plus I, plug it in, multiply it out, and that's it. Okay. Let's go back to the example that I mentioned about earlier in the week. I want to talk about the path integral along the unit circle around the function 1 over z. Now, if primitive exists, it should be something like log of z, right? The antiderivative of 1 over z is log. Derivative is in fact 1 over z. But the issue is that it's not a primitive in all of the complex plane. Well, first of all, 1 over z isn't defined at the origin. That's obvious, but 0 doesn't have to be inside of the domain. What's more of an issue is the domain where the log is defined. So remember, the log function only makes sense on a slit plane. So you have to kind of cut the plane. So I usually cut the plane on the negative real axis. Then the argument from negative pi to pi, not including the endpoints, the log function will be analytic there. But you can't have an analytic function log defined in all of the unit circle. That's the point. Okay. So f is analytic on the slit plane, and you could get close to all of the unit circle. So let's say you have a curve gamma epsilon that starts from negative pi plus epsilon to pi minus epsilon. So it's slightly below the negative real axis and ends slightly above the negative real axis. So it does this path, but not touch the slit plane. So the path integral becomes, okay, as long as we don't touch the real axis, we could use the fundamental theorem of analytic functions. So the log of gamma epsilon from negative pi plus e epsilon minus the big log of this thing. Along the path, so the log function is defined like that. So if we evaluate from the two endpoints, okay, the arg function ends close to positive pi, and it starts very close to negative pi. Sorry, that's the starting point. This needs to be reversed. So positive pi minus negative pi will actually add up to be 2 pi I. And this is the value of the path integral that we computed in the past. But if the fundamental theorem of analytic function was true, even despite the fact that the log could only be defined on a slit plane, then the starting and ending point is the same. So you should cancel each other out and we should get 0, right? So this like limitation of log being defined in all of the complex plane minus the slit plane, so connecting the 0 to negative infinity, that is a fundamental problem that you can't get around, right? So primitive kind of exists, but it doesn't exist on the entire domain that contains that the entire path gamma. Okay, so this is a very important example to keep in mind as we move forward. We'll come back to this as well. Let's do another example where the primitive does exist. So let's say gamma is any curve connecting negative pi I to positive pi I. So we can pick a path like that if you want. Doesn't matter. I don't really need to look at the value of the function between the endpoints. So if we integrate cosine along that curve, the primitive of cosine is sine. We have computed that in the past. And then we just plug in the two endpoints, right? So sine of pi I minus sine of negative pi I. Sine is an odd function, so you can pull out the negative sign. And we get sine of pi I plus sine of pi I, so 2 sine of pi I. If we plug it into the definition of complex sine function, here's what we get. Okay, all right, so we have to come back and try to answer the question, like, when can we get a primitive? Okay, that's going to be answered by a very important theorem called Gorsat's theorem. So I want to introduce you to the Gorsat's theorem. I can't prove it in this video, but we'll definitely come back and prove this next week. So let's say we have a simply connected domain D, and we have some analytic function f. Okay. Then f has a primitive in D. Moreover, the primitive is given explicitly by something that looks like the area function. Okay, so what is guaranteeing us the primitive? You look at a simply connected domain, first of all. So 1 over z has a hole at 0. So any curve kind of surrounding that hole cannot be a simply connected domain, because simply connected domain means it doesn't have any holes. So that's where this trips up for that example. But if you're working with domain with no holes, and the function you're working, the original function we're working with is analytic, right? Analytic function is going to have a primitive. So we will prove this. So idea of the proof. So this is a more involved proof. So we're going to break it up into 2 chunks. One is the Morera's theorem. So that is going to say that if you have a continuous function f on a simply connected domain, then, and also that you get the value of 0 every time you integrate along a triangular curve. So any kind of triangular curve that sits in this simply connected domain D. In that situation, you always have a primitive. Okay, so that's the first thing to prove. And then the second thing to prove, to turn it into this Gorsat's theorem, is to change the fact that you have a continuous function having this property into, if you have an analytic function, then the integral on the triangle will be 0. So that's going to be the Cauchy's theorem for triangles. Okay, so putting these 2 theorems together, right? So if you have an analytic function, integral over the triangle is 0. And if the integral over the triangle is 0, then you have primitive, right? So those two theorems together will prove Khorezat's theorem. Okay. All right, so we'll get to the details of how we might prove those things in the next videos.